Chemistry, we're on to our third and final lesson in the acid bases unit, and it's on the pH and Poh scales. So the first thing we're going to do is do a quick overview of logarithms, because a pH and Poh represent a logarithm of a concentration of hydronium or hydroxide ions. So let's just go, what do logarithms do? Most of you have probably seen them and been exposed to them in math class. Most students really don't understand what they are, what they're used for beyond that. So let's go ahead and how they apply to chemistry here. So they serve two main functions. One is they linearize, they make a straight line out of curved exponential functions so that analysis becomes possible. And two, they scale down outputs of an exponential function to make graphing possible. So we'll see what those two things mean in just a second. So let's say you're going to graph an exponential function, y equals 10 to the x, so raised to the x power. So let's define what an exponential function is. It's a function in which the variable is in the exponent. So you notice that y equals 10 to the x has a variable exponent, x. The function y equals x squared is not an exponential function. It has an exponent to it, the square, but the variable x is not in the exponent. So y equals x squared, x to the second power, is not an exponential function. Y equals 10 raised to the x power, where the variable is in the exponent, is an exponential. So very simply, if you were to plot the values of x from 0 to 5, you'd start with 0 equals 10 to the 0 power. Now remember, any number to the 0 power equals 1, not 0. It's just something you have to learn. You can do that on your calculator, and your calculator would tell you that. But if you put a 1 in, you get y equals 10 to the 1 is 10, y equals 10 to the second is 100, and then 10 to the third is 1,000, 10 to the fourth is 10,000, 10 to the fifth is 100,000. So you can see how quickly that output value y grew. By the time you're at 5, you're all the way up to 100,000. So think about trying to graph that on paper. X values go from 0 to 5, and Y values go from 1 to 10,000 or to 100,000. That's really not possible to graph that on a piece of graph paper because it goes up so fast. The range of the Y values is so great. Now let's graph the log of 10 to the X. Okay, so what we're going to do is we're going to put the values of X in for the X value there. You're going to raise it to the 10th power, and then you're going to take the log of that. And so if you put in 0, you get 0. You can do this on your calculator. If you put in 1, you get 1, 2, you get 2, and so forth. In fact, log and 10 raised to the X power are inverses of each other, just like addition and subtraction are inverses of each other. So 2 plus 4 is 6, and 6 minus 4 gets you back to 2 again. They reverse each other. Plus and minus are inverses. Multiplication and division are inverses. Well, log and 10 raised to the X power, that exponential function, are inverses of each other. So you can see that whatever you put in for X, you're simply going to get back out for Y. But notice that if you wanted to graph the data on the right, you go from 0 to 5 on the x-axis, but then again, you'd only go from 0 to 5 on the y-axis. So it would be much more possible, it's possible to graph a log of a function of an exponential than it is to graph the actual exponential, which is what you see on the left there. So that's one of the advantages of using logs. It scales things down, scales the outputs down so that you can actually graph them. Okay, so now if you were to graph the function or the data that was on the left, so here's a graph of y equals 10 to the x. So if we plot an exponential, the graph will increase so quickly that it will not fit on a piece of graph paper. It also produces a curved line. If you extended this graph to x to the 10th power, so y equals 10 to the 10th power, in other words, and if your computer screen is about the same size as mine, then that red line would reach beyond the moon. It's hard to believe that it would go up that quickly, but it would reach beyond the moon. So you just can't graph an exponential beyond about x to the second or x to the third. Even that far you can't really graph it. But if you look over on the right, that's the graph of the function y equals log of x to the 10th. So plotting x against the log produces numbers that can easily fit on a piece of graph paper. In the last slide, remember, x went from 0 to 5, and y also went from 0 to 5, so that just produces a nice straight line. It also linearizes, creates a straight line of the data. So unlike the graph on the left, this graph can easily display x equals 10 right there. So again, the two things that logs do is they straighten out your data if you have an exponential function, an exponential relationship, and they bring down the values of the y values, the output values, so that you can actually fit it on a piece of graph paper. So the pH scale is a way to express the concentration of hydronium ions. And remember, those are expressed or written as H3O plus or H plus, and it provides us a scale that's easy to read and understand. The concentrations of H3O plus ions in aqueous water solution is usually very small and is expressed in scientific notation. So example, the concentration of H3O plus ions in 1 mole per liter of acetic acid vinegar is 4.2 times 10 to the minus third. So what does that mean? It means you have 4.2 times 10 to the minus third moles of acetic acid vinegars for every liter of water. Just to give that some perspective, a liter of water is 55.5 moles. So what this means is you have 4.2 10,000ths of a mole, a very small number. 4.2 over 10,000ths of a mole of acetic acid for every 55 moles of water. So the concentrations in acids are very, very small numbers. Since the H3O plus concentration is what determines the acidity of a solution, the pH scale was devised to give chemists an easy-to-read scale of hydronium ion concentrations. The pH scale is a way to express the concentration of hydronium ions, H3O plus, that is easy to read and understand. pH is given by the following formula. So the pH is the negative log of the hydronium ion concentration. Now, as you'll see, that negative log, looks kind of scary to students, but what it simply does is make the hydronium ion concentration, which can be something like 4.2 times 10 to the minus third, it turns it into a nice number that's easy to work with and easy to kind of comprehend. So pH is the negative log of the hydronium ion concentration. P means log of. It actually stands for the power of, because you're going to see that it represents the exponent on the hydronium ion concentration. But whenever you see P, it means you take the negative log of whatever the number is. So what is the pH of a solution with a hydronium concentration of H3O plus equals 10 to the minus 9th? So the pH would be the P of 10 to the minus 9th. That's the negative log of 10 to the minus 9th. And remember what we said a log does to 10 raised to a power? It inverses it. So the log of 10 to the minus 9th is minus 9. And then the negative sign is put out in front of the word log to get rid of the negative sign. So instead of having to deal with the number 10 to the minus 9th for the concentration, you just have a nice number like 9. It's much easier to work with. When you look at 10 to the minus 9, you see two things you don't like: an exponent and a negative sign. So you want to get rid of exponents and negative signs if you can. Even scientists don't like to deal with those if they don't have to. So the log takes the negative 9 out of the exponents. It just makes it a negative 9. So log of 10 raised to the minus 9 is simply 10 to the minus 9. And the negative sign in front of the log reverses the negative sign in front of minus 9 to make the number positive 9. Similarly, the POH scale is a way to measure the concentration of hydroxide ions, OH-. Remember, hydroxide ions, OH- represent bases, a basic solution, and hydronium, what we were just talking about, represents an acidic solution. So a concentration of hydronium ions that is easy to read and understand. So POH is given by the same formula, except you replace H3O plus with OH minus. So POH is the negative log of the hydroxide concentration. P means negative log of. So what is the POH of a solution with a hydroxide ion concentration of 10 to the negative 13th? So there it's P to the P of the 10 to the negative 13th equals the negative log of 10 to the negative 13th. And again, same thing. Log of 10 to the negative 13th simply inverses and gives you the number negative 13. And then the minus sign in front of the word log reverses that to become a positive 13. So when you look at 10 to the negative 13, just repeating the earlier slide, you see two things you don't like, an exponent and a negative sign. The log takes the negative 13 out of the exponent, and the negative sign in front of the log reverses the negative sign in front of negative 13 to make the number positive 13. So the pH scale is positive numbers. So here's a look at the concentrations on the pH scale, and the pH numbers go from 0 to 14. And what 0 means is the negative log of 10 to the 0 is 1. So it's 1 molar. It's 1 mole of acid per liter. That's considered a strong acid. Anything that's 1 and less than 1 is considered a strong acid. If you go to 1 on the pH scale, you're still talking about a strong acid, and that's negative log of 10 to the minus 1. And if you just do the math on that on your calculator, you get 0.1 molar. 0.1 moles of acid for every liter of solution. That's the acid and the water mixed together. And you see as you go on up the scale, it's negative log 10 to the minus 2, 10 to the minus 3, so on, all the way up to negative log of 10 to the minus 14th for a pH of 14. And you can see that's a very, very small number. So as you go up the pH scale from 0 to 14, the concentration of hydronium ions, this is acids, gets very, very, very weak until at 10 to the minus 14th, it's almost non-existent. So this table shows the molarity and pH of different concentration of hydronium, H3O plus, and how they relate to the pH. The stronger the concentration of H3O plus ions, the lower the pH. So that kind of explains that, what seems to be a contradiction, that strong acid is a lower number on the pH scale. It's simply because that's the way it works out on the math here. So the lower the number on the pH scale, the stronger the acid. Lower numbers on the pH scale represent stronger acids. Example, what is the pH of a solution of hydronium concentration? So we've seen this question. There it is. So give the pH of the following hydronium ion concentrations. pH of 10 to the minus 6 concentration is simply going to be the negative log of 10 to the minus 6. That's 6. pH of 10 to the minus 13th concentration, negative log of 10 to the minus 13th is 13. pH of 10 to the minus 2 is 2. pH of 10 to the minus 5th is 5. Okay, now we're going to do some where you have a coefficient in front of the exponent. So let's look at this one. Over on the left, you see the pH of 10 to the minus 6. That really means 1 times 10 to the negative 6th. Here now you have 5 times 10 to the negative 6th. So think about that. 5 times 10 to the negative 6, the concentration of hydronium of 5 times 10 to the negative 6 is going to be 5 times more concentrated, more hydronium ions than just 10 to the negative 6. That means the acid is going to be stronger because you have more hydronium ions. And what that means is that the pH is then going to be lower than 6. So let me say that again. 1 times 10 to the negative 6 gives you a pH of 6. If you now multiply by 5 times the number of hydronium ions, you have 5 times 10 to the negative 6th. So that's a stronger or a larger concentration of hydronium ions which make up the acid. So it's a stronger acid. Therefore, this number is going to go down. It's going to go down below 6, not up. So even though 5 times 10 to the negative 6 is a larger number than 10 to the negative 6, the pH value, just because the way the math works out, goes down to a number lower than 6th. So there it is. It's negative log of 5 times 10 to the negative 6th. And if you were to compute that, it's going to be 5.3. So it went from 6 down to 5.3. That means it's a stronger acid. Higher hydronium ion concentration, H3O plus, means stronger acid, so the pH goes down. How about this one? pH of 3.2 times 10 to the negative 13th. Well, we see over on the left that the pH of 10 to the negative 13th is 13. This is going to be a stronger acid, 3.2 times as strong. Therefore, the pH is going to go down below 13. Okay, so there you set it up. You do this on your calculator, and that gives you 12.5. All right, pH of 1.2 times 10 to the minus 2. Now, you see 1.25 is not much bigger than 1. It's only a little bit bigger than the number 1, so it's going to make the pH go down. It's a higher hydronium ion concentration, but the pH isn't going to go down very much because 1.25 isn't that much greater than 1. And so you do the calculation on that, negative log of that number, and you get 1.9. It only went down a little bit there, from 2 down to 1.9. Finally, 10 to the negative 5th gives you a pH of 5. What about 8.91 times 10 to the negative 5th? Now that's pretty big. The coefficients have to be numbers between 1 and 9.99999, so that's getting very close to 9.999, 8.9 is. So that means the pH is going to go down quite a bit towards 4, in the direction of 4. So you plug in that number and you get 4.1. All right? So that's how you calculate these the pH values of various hydronium ion concentrations. So by using the properties of logs, we can compute the concentration of hydronium ions from the pH. In other words, go in the other direction of what we just did. And there's the formula. The concentration in moles per liter, that's molarity, that's what the square brackets mean, of hydronium ions is 10 raised to the negative pH. So using the pH 9 obtained in the previous example, we can compute the hydronium ion concentration. So H3O plus equals 10 to the minus 9. You simply take the pH of 9, put it in the exponent, and that's how many moles of hydronium ions you would have per liters of solution. That's the hydronium plus the water together. It would be 10 to the negative 9th. Okay, now here is a scale. Looks rather busy, but it takes the last scale that you saw of pH over on the left, and it adds to it the relationship to pOH. There's a step that I left out here to explain how you get from pH to pOH using pH. I'm not going to go into that here, but let's just look at the scale. If you're at 14 on the pH scale, that is a very weak acid. That's up at the very top line, but it's a very strong base. And there's the relationship is that the pH and the pOH will always add up to 14. So 14 on the pH scale plus 0 on the pOH scale equals 14. 13 on the pH scale plus 1 on the pOH scale, I'm going on the far left over to the far right, also equals 14, and so on all the way down. So you can see that at pH of 14 you have a pOH of 0. That means the pOH concentration is relatively high. It's 1 mole per liter of solution. So you see that these two are just like mirror images each other and flipped over. So on the pH scale, 0 is a very strong acid and 14 is a very weak acid. On the pOH scale, 0 up at the top is a very strong base, and 14 down at the bottom of the pOH scale is a very weak base. So you can just kind of study that for a second and see the relationship between pH and pOH. Both of them, when added together for any given solution, are going to add up to 14. So this table relates pH, pOH, hydronium ion concentration H+, and hydroxide ion concentrations OH-. Okay, there's another relationship we can derive from this formula, and that is simply that the hydronium ion concentration times the hydroxide ion concentration equals 10 to the minus 14th at 25 degrees. We always assume in acid bases we're working at 25 degrees unless told otherwise. That's basically room temperature. Okay, so take the negative log of both sides, And I'm not going to go into the log math here. You don't have to really know how to do this. And you get negative log of 10 to the minus 14th. So using the properties of logs, okay, again, we're not going to go into that. This can be written the way you see it right there. And so POH plus POH equals 14. So here's a summary of the equations for pH and POH. The concentration of H3O plus, you take 10 and you raise it to the negative pH. To get the pH value, you go in the opposite direction. You take the negative log of the hydronium ion concentration. For concentration of hydroxide, it's 10 to the minus POH, and the POH is negative log of the hydroxide ion concentration. The relationship between hydronium and hydroxide is that hydronium concentration times hydroxide concentration always equals 10 to the minus 14th at 25 degrees. And the relationship between pH and POH is pH plus POH equals 14. So here's a summary of the relationships if you want to get between any four of those variables there. So to get from H plus to OH minus, you simply know that the relationship is hydronium H plus times OH minus equals 10 to the negative 14th. To get from the hydroxide ion concentration OH minus to the POH, you take the negative log of the hydroxide, and to go back in the other direction from POH to the hydroxide ion concentration, you raise 10 to the minus pH. To get between pH and POH, you just recognize the relationship is pH plus POH equals 14. And to go between the hydronium ion H plus concentration and the pH, then you take, if you're starting with the hydronium ion concentration, it's negative log of H3O plus. That's the same as H plus, remember. Or if you want to go from pH to the concentration, you take 10 raised to the minus pH. So let's do a problem. Let's see how this works. So what is the pH of a hydroxide OH minus concentration of 5.2 times 10 to the negative 9th? So where you're starting on this chart is way up there in the upper right corner, the hydroxide ion concentration, OH minus, and where you want to end up is way down in the bottom left-hand corner where the pH is. So you can take one of two routes. I'm just going to take one of them. You could either go from hydroxide over to hydronium H plus, and then from hydronium down to pH, or you can go from hydroxide OH minus down to POH, and then from POH across to pH. So let's go ahead and do one of those two routes. So we're going to do this one. We're going to go down and then to the left. So the first thing we need to do is take the hydroxide ion concentration OH minus 5.2 times 10 to the minus 9th, and we need to take the negative log of that number to get the POH. And there you see it. We did the math on that. You get a POH of 8.3. Now you need to use the relationship that pH plus POH equals 14 to figure out what pH is. So we're going to say 14 minus the POH, which is 8.3, gives us 5.7. And so that's your final answer. The pH with that hydroxide ion concentration of 5.2 times 10 to the negative 9th, the pH is 5.7. Right there. And that takes care of this lesson and this brief unit on acid bases. Again, in AP Chemistry, this is a 3-week unit. You have a lot of time to understand this, but you go into a lot more depth than this and deal with acid bases, which are a very important topic in chemistry. So we'll see you on the next lesson.